In this video, we're going to see the final major theorem of our vector calculus course, the divergence theorem. So what are we talking about? I'm going to begin with the vector field. This is a three-dimensional vector field. It's got components m, n, and p. And the vector field I've given is a source vector field. Everything seems to be exploding out from the origin. Then the divergence is defined to be the sum of the partial derivative of the first component n with respect to x, the second n with respect to y, and p with respect to z. That gives the divergence. Okay, but what is this? Now we've actually seen divergence before in the two-dimensional case. So there we were talking about, well, the same basic type of field, a source field, but in two dimensions. And what we studied was the effect on a tiny little rectangle. If I zoomed very far in, what was the degree to which the field was crossing out across this boundary? That we call the divergence, or sometimes the flux density, and it could be measured by the partial of n with respect to x plus the partial of n with respect to y. If I think of my field, for example, as being a velocity field, and I've got some region, I'm going to be asking the tendency for the field to pour out across this tiny, tiny little path. It didn't even matter where the path was. I happened to previously put it at this sort of origin, but at any spot, you could compute the divergence. For example, even at this off-center point, there is a positive divergence because the arrows that are pointing into this little path are shorter than the arrows that are leaving from it. And so a net outflow or positive divergence. Okay, so going back to the three-dimensional case, the idea here now is instead of a little square, I have a little cube. And I'm asking, to what degree is the vector field spreading out across the boundary of this little cube? And as you investigate different points, and thus are investigating different little tiny boxes, the divergence may be different at different points along the field. Now, we can actually simplify the expression for divergence in much the same way as we simplified the expression for curl. We have a del operator, which is just the partial with respect to x in the I hat, the partial with respect to y in the j hat, and the partial with respect to z in the k hat. Then, if I take the dot product of this del operator with the field f, then what do I get? Well, precisely the divergence. The partial of n with respect to x, the partial of n with respect to y, and the partial of p with respect to z. This is an operator, which means is it something that takes a function, transforms it to another function. In this case, it takes a vector function, capital F, and spits out the vector function, the divergence of f. Now, let's go back and review Green's theorem in its divergence or flux form. When we previously talked about Stokes' theorem, we saw that Stokes' theorem was a generalization of 1/2 of Green's theorem. Today, in this video, the divergence theorem is going to be the generalization of the other half of Green's theorem. So Green's theorem in its divergence or flux form is all about the flux across a curve. So I'm imagining now I have a bona fide curve, not the small little infinitesimal one. We used to have an actual big curve. It's got a normal vector at any point. And the question is, well, how much is the field spreading out across the boundary of this curve? How much is the field aligned normal to this curve? And so what we have is this comparison between the boundary, in other words, I'm asking the outward flux across this boundary curve. And then what Green's theorem does is it relates this to a double integral over the entire region of the divergence or of the flux density. The basic argument is if I imagine cutting up the big region to a whole bunch of small little pieces, in the interior, there's a ton of cancellation. And the idea is if you have two adjacent regions, the flux from the left to the right is just the negative of the flux from the right to the left. And so adding everything up would just make that cancel. So when you get rid of all the interior cancellation of this divergence, what's left is that crossing out the final boundary, which gives us the outward flux. Now, we get to do something new because we have an improved terminology for talking about the divergence. We saw that the gradient of f, we saw that del dot f represented the divergence. So I'm just going to replace that in my formula here. Okay, now it's time finally to upgrade from the two-dimensional situation, where Green's theorem applies, to the three-dimensional situation of the divergence theorem. So what's going on? Let's look at the picture first. In the picture, I have in yellow just a vector field. Living within that vector field is a surface, and I've plotted the surface of a sphere as my example of a closed surface. And then I've also plotted a lot of red vectors. What are those? the red vectors are normal to the surface. So you have your surface. This has a whole bunch of normals at every point. And then that whole thing lives within the yellow vector field. Okay, so what happens to the actual formula? Well, the left-hand side still represents the outward flux, but it's a completely different formula than it was before. Previously, it was the outward flux across a curve, but now I'm talking about the outward flux across a surface. So the left-hand side of the divergence theorem is a surface integral. And then the right-hand side also changes. The integrand is actually the same thing. It's just the divergence. Now the divergence would be the sum of 3 things versus the sum of 2 things, but still just the divergence. But now the interior of a surface is a volume. And so it is a triple integral with respect to a volume of the divergence. So imagining that I have a domain, the boundary of the domain is going to be a surface. If I add up all through the interior, all through that volume, the tendency for the vector field to disperse at a point, for there to be divergence at a particular point, all in the middle we get interior cancellation. So then when all of those divergences are added up, everything in the middle canceling, what we're left with is just the portion that can't cancel, the portion along the boundary, which in this case is a surface, and we get the outward flux across that surface. Now, I need to be clear about what the conditions are for this theorem. So the field is nice in the same sense it needed to be nice for Stokes' theorem, but there is something new that's added on the surface. So we're talking about a surface, and the surface needs to be nice in the sense of being piecewise smooth, like a sphere or a cube. But in addition, it needs to be both oriented, which means it has 2 different sides, a continuous specification of those normals, so that I can actually make sense of outward flux, make sense of F dot n. But in addition, it needs to be closed. That is, the divergence doesn't make sense for example, a bowl with an open top. It has to be something that completely closes a region. This is somewhat analogous to in Green's theorem. We also demanded that our curves were closed here and thus contained an area. Now we're imagining our surface is closed and thus containing a volume. Alright, so that was the divergence theorem. Coming up, I need to do some examples for sure, but I also want to do a video that unifies the divergence theorem, Stokes' theorem, Green's theorem, and the fundamental theorem of calculus, and see that they're all different types of generalizations of the same thing.